Hello and welcome. In this video we're going to continue on our journey with solving second order differential equations. This one specifically will focus on homogeneous second order linear differential equations with non-zero damping. So we've already explored this idea that you can have spring mass systems without damping, and now we'll consider adding the damping term, which will result in a slightly different solution process. But let's get into some preliminaries first. These are some tools that we're going to need. So first of all is solving a system of linear equations. So suppose we want to solve this system. So by the definition or by the description, system just means there's more than one equation to be solved. And they are linear, obviously, because you could get them in the form y equals mx plus b. And what we want to do is we want to find a solution, a pair of values, x and y, that make the equations simultaneously true. So you can look at this and you can say, well, 5 plus 5 equals 10. And so x equals 5, y equals 5 satisfies the first equation. But it does not satisfy the second one because 2 times 5 plus 3 times 5 is 25 and not 23. So 5 and 5 don't quite work. There are a couple of ways you can solve this. One way is to drop both of the equations into graphing application and find their intersection point. So here we see that 7, 3 is the point that both equations share in common. And so geometrically, the solution is the point that they have in common, which is the intersection point. So that 7, 3 is on both lines, therefore 7 plus 3 equals 10, and 2 times 7 is 14, 3 times 3 is 9, 14 plus 9 is 23. So that point 7, 3 makes both equations true. Now that's one way to solve it, is to graph them and find the intersection point. The other way is to, one other way you may have seen before is called substitution. And so if you solve one of the equations for one of the variables, for example, x plus y equals 10, if we simply subtract y from both sides, we get x is equal to 10 minus y. Now what we can do with that is, because this x is the same as this x down here, I can actually substitute in 10 minus y in for x. So let's go ahead and do that. 2 times x, so this is 10 minus y. And now you can see that we've obtained an equation that now only depends on y. So we do some distribution, 20 minus 2y plus 3y equals 23, which gives us 20 plus y equals 23, or y equals 3. Now at that point, once you find the y value that both equations have in common, you can plug y equals 3 back into either of the two equations and solve for x, but this one's already solved for x, so why not just say x equals 10 minus y? So since y is equal to 3, we're going to go ahead and substitute that out for 3, and 10 minus 3 is 7. So x equals 7, y equals 3 is the solution. Now, if you had plugged in y equals 3 up here, let's say 2 times x plus 3 times 3 equals 23, and solved for x, you would get exactly the same answer. You get 2x equals 14 and x equals 7, which is the same answer we got here. So once you find one of the values that they share in common, the other value corresponds to the value you've already found. Therefore, it's not important which one you plug it into. Anyway, but the point is, this is unnecessary. It's just extra algebra. We don't want to get tied up in that. So you can also just enter the two equations in, separated by a comma, into Wolfram alpha, and you get the solution that shows up. It even shows you a beautiful graph of those intersection points. All right, so now we're ready to go on, because we're going to need to solve a system of equations. As you've seen with velocity and initial position, we had two equations. Fortunately for us, those reduce down very easily to solve for K1 and K2, but sometimes you get a system of equations where you do have to find the point that both equations have in common. So consider a spring mass system. Now we're going to assume that we have a spring constant of 2. If we're in the metric system, this is measured in newtons per meter. So the amount of force that the spring applies for every meter of displacement. And you can also see this here, and just in case you want a little bit of intuition behind this, the spring force is negatively proportional to y. So that means that if you want to determine your spring force and k is 2, now you just have to think about your displacement. So you can see that the spring force, which is measured in newtons, is going to be -2 times the displacement. So for every 1 meter you increase y by, the spring force will get bigger by a factor of 2 newtons. So that also helps justify this newtons per meter. Now this is the force per unit of velocity. So the faster this spring mass system is moving, the greater the decrease in speed that will be caused by the damping coefficient. So it's going to slow this spring mass system down. So ideally, if you kind of imagine that this is the spring mass system, and here you have a mass, and this thing is going to be kind of going, let's say it starts by going down, and then it goes up, and then it goes down, and then because of the damping factor, we probably expect this mass to slowly stop oscillating and come to a rest. And then we have m equals, not 0, m equals 1. And that would be measured in kilograms. Now these are not necessarily realistic values. Right now we're just learning how to work with these. Obviously having 1 kilogram mass may be a lot heavier than our spring mass system, or maybe not heavy enough. So then when we plug in, here we have, this is b over m, and this is k over m, so 3 over 1 and 2 over 1. Now, unfortunately for us, because now we have this middle term in here, sine and cosine don't work. And the reason these won't work is because, for example, if we said y1, our initial guess is of the form y1 equals sine of even something t. So even if we didn't know what that was going to be, what constant argument we're going to have there, we could say, well, y prime equals b cosine of bt. And y1 double prime is equal to -b squared sine of bt. Now the problem we're going to have when we come over here and we plug these components in is that you're going to see that now we have a mixture of sines and cosines. So y double prime is -b squared sine of bt plus 3b cosine of bt plus 2 sine of bt equals 0, and there's no way these three things can add up to 0, because remember, sine, the basic sine function is going to look like this, but the cosine function looks like this. So these guys are not in the same phase, and therefore they're not always going to be able to sum to 0. So these will not equal 0 because of the fact that we have 2 sines and we have 1 cosine in here, and those are not like terms, so they will not combine. So the only other function that we know of, so barring this, if this term were missing, sine and cosine would work. But with that term there, sine and cosine will not work, so we resort to things that we already know. Well, what kinds of things can we add to its derivatives, or what kind of function can we add to its derivatives, and they're all like terms? Well, exponential functions, when you take their derivative, the derivative of an exponential is always another exponential with the same exponent. Therefore, let's try this approach. Let's say, you know what, sine and cosine aren't going to work because the first derivative is going to not be able to cancel with the function and its second derivative. So we're going to use the method of undetermined coefficients. Now this just means that we don't know exactly what value of r will work here, but with y equals e to the rt as the base function, assume that y of 0 equals 0, y prime of 0 equals -1. Graph the solution. Is it what we would expect? Okay, so we know from our equation it's y double prime plus 3y prime plus 2y equals 0. Now, our guess is of the form y equals e to the rt. Now, the beauty of this is that if the guess is wrong, the mathematics simply will not work out. Just like up here, we said, oh, it's going to be sine of bt, and then we run into a problem. We can't actually find a value of b that will cause these three functions to add up to 0. So if something goes wrong, if this is the wrong guess, the mathematics will let us know. So the derivative of e to the rt is r times e to the rt by the chain rule. And the second derivative of that is r times r, which is r squared, e to the rt. So now what I'm going to do is I'm going to solve for r. Solve for r. And the way in which we're going to do that is we're going to say, well, y double prime is r squared e to the rt. Now we have that 3y is going to be 3 times r e to the rt. So 3r e to the rt. And then 2y, which is this guy here, that's going to be 2 times e to the rt. So we'll have plus 2e to the rt. And we know that these three things have to add up to 0. Now you see that this is going to be possible because they're all common, they're all like terms, right? This has the e to the rt, this has e to the rt, this has e to the rt. Here I have r squared of them, here I have 3r of them, here I have 2 of them. So if I'm going to add like terms, I'm going to add their coefficients. Again, another way you can view this as is if you factor out e to the rt, you get r squared plus 3r plus 2, and that all equals 0. Now again, another way of thinking about that is I have r squared copies of e to the rt plus 3r more plus 2 more, and so we just approached it via factoring, but it is simply a matter of adding the coefficients together. Now e to the rt, if you think about that function, the only way two things multiplied together can be 0 is if one is 0 or the other is 0. Now e to the rt never equals 0. Now that's because even e to the rt does one of a couple of different things. It either grows exponentially or it's going to decay exponentially. So that could look like this. All right, so those are kind of our two options there. And if it grows, then obviously it's not going to approach 0. And there's no number you could raise something to in order to get 0. So e to the 0 is 1, e to the negative 1 is 1 over e. So these functions will never equal 0. So anyway, the point is the only way for this product to be 0 is if r squared plus 3r plus 2 is equal to 0. Perfect. Well, I know how to solve this. This is a quadratic function. This is a quadratic function, which means I can solve it one of a couple of different ways. I can use the quadratic formula. So you can use quadratic formula, which recall that to solve this equation, it would be negative b plus or minus the square root of b squared minus 4ac over 2a. Another way to solve this is to graph this parabola. This is going to be a parabolic function, and then find out where the roots are, where this function intersects the x-axis. So we were looking for 2 points. The other way you could do it is just by using some sort of Wolfram alpha or something, type this in and it will solve it for you. So if you just typed in r squared plus 3r plus 2 equals 0 into Wolfram alpha, that would solve it as well. So I'll just put a third here, Wolfram alpha. And you would just type in r squared plus 3r plus 2 equals 0. And even a fourth way that we haven't described is factoring. Now, if you're not sharp on your factoring skills, you may not want to try that, but this one does actually factor nicely. R squared plus 3r plus 2 factors into r plus 2 times r plus 1 equals 0. And the trick behind factoring here is these two constants have to multiply to give me 2 and have to add to give me 3. And so that works out. So I get r equals negative 2 and r equals negative 1. Now I don't want to treat those as the same, so I'll call this r1 and r2. Which one's which does not make any difference. So that means I have two solutions. As we've stated before, we said that second order equations have two solutions. And guess what? This is why. Because whenever you go about solving equations like this, you're going to end up solving a quadratic. So we have y1 is equal to e to the negative 2t, so that's r1, and y2 is equal to e to the negative 1t. Now by superposition, by the superposition theorem, we know that if you have a homogeneous differential equation and you find two solutions, any constant multiple of the first solution plus any constant multiple of the second solution is also a solution. And there is our spring mass system solution. Now what we need to do is, sorry, this kind of look a little messy. Now we just need to satisfy the initial conditions. And to do that, we see that our initial position is 0 and our initial velocity is -1. So remember, this is position. In the same way, we need to find the velocity function, which is the derivative of the position function. So the derivative of this will be -2 k1 e to the -2t minus 1 k2 e to the -t because of the chain rule. And now we can plug in our initial position, which is 0 at time 0, plus k2 e to the -0. And our initial velocity is -1, so we'll plug in -1 for the initial velocity, -2 k1 e to the -2 times 0, minus k2 e to the -0. Now the nice part about these exponentials is that e to the 0 is 1, so we have two equations. This one right here is going to give me 0 equals k1 plus k2 for this equation, and this one will give me -1 equals -2 k1 minus k2. And this system of equations right here is exactly what we were doing in our preliminaries. We want to solve this system of equations so that we can figure out what k1 and k2 are. So I'll go ahead and do this in Wolfram alpha. And here you can see that now, entering the equations in, I just like to type k1, k2. Sometimes you work trying to do an underscore, makes Wolfram alpha give you some odd output. Just make sure it interprets it. These brackets mean set. It's the set of equations. And Wolfram naturally knows that if you give it a set of equations that you're often looking for a solution. So we get k1 equals 1, k2 equals -1. So that means our final solution is going to be y equals k1 e to the -2t plus k2, which is -1, e to the -t. And this is how our spring mass system, its position, occurs over time.